So I'm going to talk about HSDS, the Highly Scalable Data Service, also known as KIDA in our commercial implementation. And what it is HDF5 designed for the cloud. So here's the big idea. Rather than have a library that just works on a single system, you have a web API. And rather than using files, we utilize object storage. And rather than being limited to a single computer, we take advantage of elastic compute. So we can utilize multiple computers for computation. And since we don't want everyone to have to rewrite their HDF applications, we provide compatibility. So your existing applications just work with HSDS. Let me define cloud. So the cloud isn't necessarily AWS, Azure, or Google Cloud. You can think of a cloud as utilizing a common set of technologies. And these technologies can either be in a public cloud or they could be in a private cloud. And basically, these technologies consist of an object storage system, a way to manage a set of containers, and a way to scale up and down those applications. So the advantage of this model is that you can scale your application beyond the capacity of a single server. You have more efficient utilization of your hardware resources. Your applications are more robust, right? So a single server won't affect any running application. And if you have this architecture, you easily can port to the public cloud, if need be. So high points about HSDS. Okay, we have a RESTful interface to HDF5. We use either S3 storage, Azure Blob storage, or any one of a number of on-prem object storage systems like OpenIO. It runs as a set of Docker containers, and it's feature compatible with the HDF5 library. I would say it's more than feature compatible that we have features in HSDS that don't have analogs in the library. And it's implemented in Python using async IO. Async IO is a method of parallelizing multiple IO threads, but rather than using different system threads, we just are able to move on to different tasks when certain tasks are waiting for IO. So I mentioned object storage. What's the big deal about it? Well, it has lower costs compared to NAS systems, and especially parallel file systems like Lustre or GPFS. It's easier to scale up, right? So if you need more storage, you just bring in more servers and you have more storage. You reduce bottlenecks that you may have with POSIX file systems. There's no limitation to the size of a file. So, for example, we created HDF5, air quotes, files with HSDS that are hundreds of terabytes in size. And we enabled this cloud-native architecture that I was talking about. And it enables you to move your on-prem systems to public cloud systems as need be. So if we like object storage, what are the challenges with using object storage in HDF? Well, namely, it's not POSIX. Everything about the HDF5 library assumes POSIX, meaning that you have the ability to modify portions of a file without overwriting the entire file, which is not the case with object storage. Another challenge is that it's higher latency typically than POSIX storage. It's not necessarily read-write consistent. Getting high throughput requires some trickery. So we came up with a new implementation to support this HDF data model using object storage. And the idea is basically a sharded representation of the HDF5 data model. An HDF file consists of groups and links and data sets. We take these and we store each of these objects as a single object store object using JSON. And then for the bulk of the data, we take each data set and it's divided up into chunks. And each of those chunks is stored as a binary blob. So for example, let's say this grid represents a data set. We divide it up along these bold lines, and those are the chunks. And each of those chunks gets stored as an object in the storage system. Now, what happens when, say, an application needs to read this yellow region? Well, that crosses 6 different chunks, and it would be quite a challenge for applications to pull out those 6 chunks and put together the section it wants to read. But the service does this for us, right? We just say, service, I want to read the selection, and that data flows back to the client. This is implemented, again, using containers. And we have 2 types of containers. There are service nodes that take application requests, and there are data nodes that do the actual reading and writing to the storage system. And each data node gets assigned to a virtual partition of the object store. This allows each data node to have a live cache of its partitions objects. And what that means is, one, that we get around the lack of read-write consistency. 2, that access is much faster once you've already read in a given object. That object can live in an LRU cache on the data node, and subsequent access to any data in that object much faster. The other aspect is that service nodes can multiplex requests to the data nodes. So if a request, say, covers a number of chunks, each of those chunks becomes a request to a data node. So you can have, for a single client request, you can have multiple data nodes working in parallel to perform that operation. So just to run through some of the HSDS features. Clients basically interact with the service using the REST API. We have SDKs for C and Python. Potentially, we could have an SDK for Java or .NET, but we haven't gotten to that yet. Applications read and write just the need compared to, say, transferring an entire file to get the data. We support compression. We have authentication using either HTTP basic auth, Azure Active Directory, or OpenID. And we have authorization. So authentication is basically saying, verifying the system you are who you say you are. Authorization is, do you have the right to perform a certain operation, say updating a file? The authorization is by access control lists. So these access control lists control who can do what to a given file. And audit trail is something that's baked into a service, right? So any request to a service gets logged, and we know who did what operation to what file. Performance is scalable. So as we have more containers, we have more RAM available for caching. We have more parallelization, right? So adding more nodes means more performance. If you want to run more nodes than you have capacity for in a given server, you could use a system like Kubernetes, which lets you run those nodes over multiple machines. So it's very important to have scalability, unlike with the library, where each client is talking to its library on its machine. Here, potentially, you have hundreds or thousands of clients talking to a given server, and you want that server to be able to robustly handle these requests. So we have HSDS is able to run on a variety of different systems, right? So for managing the containers, you can use Docker, Kubernetes, Amazon EKS as your Kubernetes service, our DCOS. And we can mix and match that with different storage systems. You can have normal POSIX storage. You can have S3, Microsoft Azure Blob Storage, OpenIO, Ceph, etc. So let me talk about the client-side architecture. And I forgot to update my animation, but starting here. So on the right, imagine we have our HSDS service. So this could be running somewhere else, somewhere on the internet. On the left, you have different ways clients can connect to that service. So one way that is dramatically different than you have with a library is you can have a web application. So you can have a web page using Ajax that is fetching data dynamically from the server. So this has certain advantages, right? You don't need to write a desktop UI to access data. You can write a web app that runs on any system that supports a browser. If you have, say, a Java.NET application, it can use the JNI pinvoke to the library. And now the HDF library supports a plugin called the RESTfile plugin, and that goes to the REST API, which goes to the service. So here the advantage is that your existing application doesn't really know that it's not talking to local files on its server. It's just talking to its normal library, and that library is converting those library API calls to HTTP requests that are going to the server and back again. Same thing works more directly for C or Fortran applications. They talk to a library, this plugin is invoked, and as far as the C or Fortran application knows, it's just working with a normal HDF5 API. For Python applications, we have a special Python package that doesn't go through the library, but directly goes through the REST API to the server. And we have command line tools, which I'll talk about later, that let you do certain operations. So for Python, we have a few operations that are extensions to what you can do normally with a library. For instance, the HDF library doesn't have support for listing HDF files and directories or removing files, etc., because all those operations are handled with the POSIX API. But we need those for accessing content on the server. So we have APIs for like listing content folders, getting setting ACLs, and we have ability to run database-like queries over datasets. For R, a SDK has been developed outside the HDF Group that uses R as the client language. And this is still in the prototype stage, but I think it's reflective that it's certainly possible to extend this over different programming languages. So a little bit about the RESTful. So it's a plugin layer for HDF5. You keep the same public API, but you can support different backends. So the RESTful is not the only vol. We have other vols in development for different architectures. The RESTful substitutes REST API calls for each I/O action. C and Fortran applications are able to run as is, and C# or Java applications can use pinvoke or JNI to access the HDF library, which in turn accesses the RESTful. So some of these command line tools are like HSLS to list contents and folders, HSTouch to create a file, hsload and hsget take an ordinary HDF file and do the sharding to upload it to the server, and hsget would reconstitute that file as a normal HDF file. So you have this ability to round trip existing HDF files to a server and back again. And hsACL is used for creating or updating the access control list. So I mentioned we take a file and we shard it into the specific schema that we use in HSDS. But what if you have, a few petabytes of HDF files? It's quite imposition to have to copy all that storage and convert it to this other schema. So to support these situations, we're able to have read access to existing HDF files. And we do this by skimming off the metadata of those files, keeping the traditional HDF file as an object storage object. And then whenever data from a data set needs to be accessed, we just kind of, using the S3 RangeGet API, we just kind of reach in and pull out that piece of data. So you have normal access to these files. The only thing you don't have is support for modification of those files, which could be a feature if you want to make doubly sure that, say, a set of reference files never get modified. So now let me talk about a very preliminary speculation of what ADF as a service could look like. So we have HSDS, HDF as a service. How can we go from that to ADF as a service? So, and I have three possible approaches from least effort to greatest effort. So approach one would be that you have HSDS set up, you use the ADF library, it talks to the HDF5 library, it talks to the RESTfile plugin, which talks to HSDS. So that's the least amount of effort. We'll just need some verification that existing ADF applications work through this pipeline. It's compatible with using file-based storage. The negatives are that we still don't have good support for data description. We don't get a R Python interface. Debugging the calls from Java to C to HP to the Python-based service is a little brittle. Approach two is enhance HSDS to support specific features that are needed for ADF, for example, the ontologies. Here, the pro is that you have just one service. It's potentially more efficient than what we have now using the library. You store all the ADF data within a given container. Your client library becomes smaller because it doesn't have to do some of the heavy lifting that is needed now with the ADF library. Cons is we'd have to research how much effort it is to add these capabilities. I mean, first define the capabilities and then figure out how much effort is needed. And we still don't get a R or Python interface. Approach three is you create a ADF service with its own REST API. So now your clients are the simplest, right? Because they don't need to do any real work. They're just taking calls and whatever the client application language is, converting those to HTTP requests. The ADF service itself doesn't need to implement everything. It can delegate. So for, say, data cubes, the service could call HSDS. For ontologies, it could call a service designed for ontologies like Jelenak. So you have ability to reuse existing software that's designed for those specific tasks. Cons is this is more effort. You'd have multiple servers to manage now on the server side, and there'd be no kind of drop-down ability, right? So applications wouldn't be able to, say, use the HDF5 API directly if they wanted to. They would have to always go through the ADF service layer. Okay, so that was a very quick run-through of HSDS. I'm available. Send me an email or set some time to chat if you'd like to deep dive into any particular aspect of this in more detail. So finally, I guess we have a few minutes for questions. Thank you.
Great, thanks, John. So we do have the opportunity to take some questions. I forgot to mention at the top of the hour, but just to remind everyone that this session is being recorded, just so you know. If you do have any questions, you can type them into the chat box. You could also use the raise your hand function and go to webinar, and we can answer those for you. Jamie, have we gotten any questions so far?
Yeah, John, there was a question which I sent to you. I don't know if you can see it on your screen, otherwise I can read it.
Let's see. It says, is it possible to access data in Object Store in a serverless manner? Yes. So the data in the Object Store is there, and one of the nice things about the HSDS schema is that the metadata is just stored as JSON data. So if you would like to go around the server, so to speak, it's very easy, relatively, to pull out that JSON object and have a application use it directly. Of course, this does the end run around any kind of the ACL-based security. So this will only be suitable for applications that have read access to the storage system.
Great. Any other questions for John?
Yep, let me just send it over to him.
Perfect.
I got it. Do you have advice for getting started for HDF5 users who have no experience with cloud programming? It kind of depends on what you want to do, right? If it is you are an HDF5 application programmer, it's very easy to get started using HSDS because, like we talked about, it's the same API. And we have a system called Kita Lab that lets you go to a kind of Jupyter notebooks in the cloud and start using a service directly. If you are in the role of setting up systems, servers to run, there's a wide variety of tutorials and such. I'd recommend watching some of the tutorials about Kubernetes because I think those kind of broadly touch upon how to set up, complex systems of servers rather than, doing a single task in the cloud.
Great. Well, thank you, John. So I think now, is there one more?
I am the first one. Please more info on Kita Lab. Yes, I can share a link to it. Let me... One second. Yeah, if you just Google Kita Lab, maybe not. Okay, I'll send a link to Matthew in a bit.
Great. Great, thanks again, John.